Somewhere out past the orbit of Neptune, drifting silently through the dark, there's an object that scientists still cannot fully explain. It did not behave the way it was supposed to. It did not look the way it was supposed to. And to this day, nobody can say with total certainty what it actually was. Ita's name is ʻOumuamua, and when it swept through our solar system in 2017, it left some of the sharpest minds in astronomy completely confused. The story begins on October 19th, 2017, at a survey telescope sitting on top of a dormant volcano in Hawaii. The telescope, called Pan-STARRS, was doing what it always does, scanning the night sky for anything that moves against the fixed backdrop of stars. That night, an astronomer named Robert Warwick noticed something strange in the data. A faint point of light was streaking across the frame far too quickly to be anything orbiting our sun in the normal way. At first, researchers assumed it had to be a comet or an asteroid, something ordinary that simply had not been cataloged yet. Within days, that assumption fell apart completely. When scientists calculated its trajectory, the numbers did not make sense for anything native to our solar system. The object was moving on a hyperbolic path, meaning it was not looping around the sun the way planets, comets, and asteroids do. It had come from outside our solar system entirely, and after its one and only pass by the sun, it was going to leave again forever. This was the first time in recorded history that astronomers had confirmed an object visiting us from interstellar space. It was given the formal designation 1I 2017 U1, with the I standing for interstellar, and it was later named ʻOumuamua, a Hawaiian word that roughly translates to a scout or a messenger reaching out from the distant past. The choice of name was deliberate. Hawaiian astronomers involved in the discovery felt that a Hawaiian name suited an object found by a telescope on Hawaiian soil, and ʻOumuamua carried a meaning that fit the moment perfectly. A scout sent ahead, a messenger arriving from a distance to let us know something else is out there. It was a poetic choice for an object that would go on to raise more questions than almost anything else discovered in modern astronomy. From the very beginning, everything about it seemed to break the rules. Telescopes around the world turned toward it, trying to squeeze out every possible detail before it slipped away into the darkness for good. What they found only deepened the mystery. Most comets and asteroids are roughly round or slightly irregular in shape. ʻOumuamua was not. Based on how its brightness changed as it tumbled through space, scientists calculated that it was extremely elongated, possibly 10 times longer than it was wide. Some models suggested it looked like a cigar. Others suggested something closer to a flattened pancake. Either way, nothing like it had ever been observed before, and nothing has been observed since that matches its exact shape. Then came an even stranger discovery. As ʻOumuamua sped away from the sun, it should have followed a predictable path shaped only by the sun's gravity. Instead, it sped up slightly more than gravity alone could explain. Comets sometimes do this because they are made of ice that turns directly into gas as they warm up near the sun, and that outgassing acts like a tiny rocket thruster, nudging the comet off its expected path. The problem was that ʻOumuamua showed absolutely no visible signs of a coma or a tail, the glowing cloud of gas and dust that normally surrounds an active comet. Every telescope that looked for that signature came up empty. So how could something accelerate like an outgassing comet while looking nothing like one? That single contradiction, extra acceleration with no visible outgassing, became the central puzzle that scientists have spent years trying to solve. It is the reason ʻOumuamua refuses to fit neatly into any known category, and it is the reason the debate over what it actually was has never fully settled. There was another oddity too, one that rarely gets as much attention as the shape or the acceleration, but that quietly bothered researchers just as much. ʻOumuamua was not spinning smoothly on a single axis the way most asteroids do. It was tumbling, rotating chaotically along multiple axes at once, completing a full cycle roughly every 8 hours. Objects usually settle into a stable spin over time, so a tumble like this suggested that something violent had happened to it in its past, perhaps a collision, or a close gravitational encounter with another body, long before it ever entered our solar system. Combined with its brightness swings, some 10 times brighter at certain angles than others, that tumbling motion is part of what convinced scientists the object had to be unusually elongated rather than simply irregular in shape. Its color added yet another layer to the puzzle. ʻOumuamua appeared distinctly reddish, a shade often associated with objects that have spent a long time exposed to cosmic radiation, their surfaces slowly transformed by particles bombarding them across unimaginable stretches of time and distance. That reddish tint is common among certain icy bodies in the outer reaches of our own solar system, which gave some scientists another reason to suspect ʻOumuamua had spent an extraordinarily long time drifting through the emptiness between stars before it ever crossed paths with our sun. Some researchers proposed that the object might be made largely of frozen hydrogen ice, a material so fragile and so easily vaporized that it could explain the acceleration without producing any visible dust or gas that our telescopes could detect. It was an elegant idea on paper, but later studies argued that hydrogen ice would evaporate almost instantly under the radiation bombarding interstellar space long before Oumuamua could have survived the journey between stars. That theory largely fell out of favor, but it opened the door to a wave of alternative explanations, each trying to account for the same strange behavior in a different way. One of the more compelling ideas came from researchers who suggested that Oumuamua might be a fragment blasted off from something like a Pluto-sized world in another star system, essentially a chunk of what scientists have started calling an exopluto. According to this theory, if the object were made largely of frozen nitrogen ice, the kind of ice found on the surface of Pluto itself, it could explain both its unusual elongated shape and its odd, unexplained acceleration without needing anything exotic at all. Under this model, nitrogen ice, evaporating gently off the object's surface as it warmed near the sun, could have provided just enough thrust to speed it up, while being subtle enough that it never produced an obvious visible tail. It is a fully natural explanation, but the fact that scientists needed to invent an entirely new category of object just to make the numbers work says everything about how strange Oumuamua really was. And then there is the theory that captured the public imagination more than any other, the idea that Oumuamua might not have been natural at all. A Harvard astrophysicist argued that the object's unusual acceleration could be explained if it were artificial, something closer to a lightweight solar sail than a lump of rock or ice. A thin, high reflective structure would be pushed gently by sunlight itself, producing exactly the kind of extra acceleration that was observed, all without needing any visible gas or dust. It was a bold claim, and it was met with plenty of skepticism from much of the scientific community, but it could not be completely ruled out using the limited data collected before the object disappeared from view. Not everyone in the scientific community was willing to entertain the artificial explanation, and plenty of researchers pushed back hard against it. Most astronomers studying Oumuamua argued that every observed behavior, the elongated shape, the tumbling, the reddish color, and even the unexplained acceleration, could still be explained through entirely natural processes. If the right combination of unusual conditions applied, they pointed out that extraordinary claims require extraordinary evidence, and that a single, brief, incomplete set of observations was a thin foundation for concluding that humanity had detected alien technology. The disagreement became public and, at times, surprisingly heated, playing out in scientific journals, conference talks, and eventually popular books aimed at a general audience. It was a rare moment where a genuine scientific debate broke out of academic circles and became dinner table conversation around the world. Because that possibility could not simply be dismissed, a team working with the Breakthrough Listen project decided to take it seriously enough to actually check. They pointed one of the most sensitive radio telescopes on Earth directly at Oumuamua, scanning across a huge range of radio frequencies, sensitive enough in theory to pick up a signal no stronger than an ordinary cell phone. After hours of careful listening, they found nothing. No transmission, no repeating pattern, no evidence of anything artificial broadcasting from the object. For some scientists, that silence was reassuring. For others, hoping for a genuine encounter with something built by another civilization, it was a quiet disappointment. Either way, it did not fully close the debate, because an object can be artificial without transmitting anything at all. What makes Oumuamua so difficult to study, and so unlikely to ever be fully explained, comes down to simple timing. By the time astronomers realized what they were looking at, the object was already leaving. It had made its closest approach to the sun weeks earlier, and every day that passed, it grew fainter and farther away. Telescopes only had a narrow window, roughly a few weeks, to gather every scrap of data they possibly could before Oumuamua faded beyond the reach of even the most powerful instruments on Earth. There was no chance to send a spacecraft to catch up with it. There was no second look scheduled for later. Whatever data was collected during that brief window is, and will likely remain, all the information humanity will ever have about this particular object. As the months went by, Oumuamua continued its outward journey, crossing the orbit of Mars, then Jupiter, then Saturn, before eventually passing beyond Neptune, the same region of the solar system where it now sits in our story. No telescope on Earth or in space is powerful enough to observe it anymore. It is simply too small, too dark, and too far away. Scientists studying the object openly admit that we will likely never fully understand exactly what it is or precisely where in the galaxy it originally came from. Its journey will eventually carry it toward the outer edge of our solar system's boundary, the heliopause, before it continues drifting silently into interstellar space forever, carrying its secrets with it. The discovery of Oumuamua did more than just puzzle scientists for a few months. It fundamentally changed how astronomers think about our galactic neighborhood. Before 2017, the idea of interstellar objects passing through our solar system was mostly theoretical, something models predicted, but nobody had ever actually confirmed. Oumuamua proved that these visitors are real, and more importantly, it suggested that they might not be rare at all. Researchers have since estimated that several interstellar objects likely pass through our solar system every single year, most of them simply too small, too dim, or too poorly timed for our current telescopes to catch. That realization sparked a second wave of scientific interest. One focused less on what ʻOumuamua specifically was, and more on what its existence implied about the universe as a whole. If interstellar objects are common, then some of them must occasionally collide with planets, including our own. That raises a genuinely unsettling question. Could material from other star systems have been slamming into Earth for billions of years? And if it has, could it have carried something more than just rock and ice? Could it have carried the raw ingredients for life itself? This question connects directly to a real scientific idea called panspermia, the theory that life, or at least the building blocks of life, might be scattered throughout the galaxy and occasionally transported from world to world by asteroids, comets, and interstellar wanderers like ʻOumuamua. The idea suggests that certain hardy microorganisms, the kind capable of surviving brutal extremes of radiation, cold, and vacuum, could theoretically endure the journey through interstellar space, hitching a ride inside chunks of rock and ice until they eventually collide with a planet capable of supporting life. It stands in contrast to the leading rival explanation for how life began on Earth, the idea that biology arose entirely on its own from non-living chemistry already present here at home. Testing panspermia directly is notoriously difficult since it depends on so many unknowns stacked on top of each other. Could microorganisms actually survive the radiation released by a nearby supernova explosion during their journey? How many objects like ʻOumuamua would need to strike a young Earth before the first evidence of life could appear in the fossil record? Nobody has clean answers to these questions. ʻOumuamua was not the last of its kind. Just 2 years later, in 2019, a second interstellar object was discovered, a comet named 2I Borisov. Unlike ʻOumuamua, Borisov behaved exactly the way scientists expected a comet to behave. It developed a clearly visible tail and coma as it approached the sun, confirming immediately what it was made of and removing almost all of the ambiguity that had surrounded the first visitor. In many ways, Borisov served as a kind of control, a normal interstellar comet that helped scientists understand just how unusual ʻOumuamua's behavior had really been by comparison. Then, in the summer of 2025, a third confirmed interstellar object streaked into view, discovered by a next-generation survey telescope in Chile, and eventually designated 3I Atlas. Because newer instruments caught it much earlier in its approach, scientists were able to track its path and study its composition far more thoroughly than they ever could with ʻOumuamua. That third discovery only reinforced something astronomers have increasingly come to accept, that interstellar visitors are not some rare cosmic fluke. They are a regular expected feature of how our galaxy works, and improving technology means we are simply getting better at catching them in time. That improvement is already accelerating. The Vera Rubin Observatory in Chile, a project that spent years under construction, achieved first light in 2025 and has since begun its 10-year survey of the entire visible sky. Over the coming decade, it is expected to catalog millions of objects throughout the solar system, from asteroids and comets to, almost certainly, a growing number of interstellar visitors caught earlier and studied more completely than ʻOumuamua ever was. Scientists are hopeful that the next truly strange interstellar object will not simply vanish into the dark before we have a real chance to study it properly. In fact, researchers have already begun designing missions specifically built for that moment. Another idea, developed independently by a nonprofit research group, imagines a similar rapid response concept aimed at reaching an interstellar object while it is still close enough to study in detail. None of these missions currently have a firm launch date, but the research behind them is treated as a necessary first step. Groundwork for the day when a spacecraft actually needs to move on short notice. Picture a scenario where a new visitor streaks into our solar system, and at first, astronomers assume it is simply another wanderer, the same way ʻOumuamua and the two visitors that followed it turned out to be. We have grown used to the idea of unannounced guests passing through, even though none of them have ever shown a single sign of being anything other than dead, silent material. But what if the next one moves in a way that does not match ordinary orbital physics? What if it slows down, or changes course, or settles into a stable orbit instead of continuing on its way out? Nobody can say whether an encounter like that will ever actually happen, but the mere fact that ʻOumuamua once looked strange enough to make serious scientists ask that question at all says something about how much uncertainty still surrounds these visitors and how unprepared we currently are to answer it if the moment ever arrives. Even with everything scientists have learned since 2017, the honest answer to what ʻOumuamua actually was remains incomplete. Was it an unusually shaped chunk of nitrogen ice blasted off a distant dwarf planet millions or billions of years ago? Was it a fragile relic made of exotic ices that evaporated in ways we have never directly observed before? Or was it something else entirely, something that does not fit any model scientists have proposed so far? Nobody can say for certain, and because the object is already gone, drifting silently beyond the reach of our instruments, that uncertainty may never be resolved. What ʻOumuamua left behind was not an answer. It was a reminder of how much remains unknown about the space between the stars, and proof that our solar system is not as isolated as we once assumed. Somewhere out there right now, more objects like it are almost certainly moving through the dark, unnoticed, unnamed, and utterly indifferent to whether we are watching. The only real question left is whether the next one will move slowly enough and stay close enough for long enough for scientists to finally get the answers that ʻOumuamua took with it when it slipped past Neptune and disappeared into interstellar space for good.